grounding and bonding session from Frank Peeples. So Frank is currently with HPT Communications representing McLean Power Systems. He has been with HPT for a little over a year, working in sales and technical support. Frank retired as an operations director for outside plant in the Texoma region of Optimum in July of 2023, after 41 years of service and through numerous company acquisitions. He worked with multiple MSOs, including Midwest Video, McCaw Cablevision, Cook Cablevision, TCA, Cox, Suddenlink, ATS, and Optimum. So we'll hand it over to Frank. Frank, you ready?
I am ready, Jason. Can you hear me all right?
Yep, all good.
All right, good deal. Thank you for the introduction and welcome, and thank you everyone for joining this morning. This morning I'm going to be covering a bonding and grounding review. I know many of you that have been in the industry a long time. This is nothing new. This is something we've been doing for a long time, but usually even seasoned veterans can pick up a few tidbits from going through the review. So hopefully everyone will get something out of this morning. I just wanted to sort of set the stage. This is a somewhat detailed presentation that it takes a bit of time to get through. What I'd like to do this morning, there are several topics in the presentation that I'll touch on early, and then later on we'll cover in more detail. So I'm sure you'll have questions along the way. What I'd like to do is just, if you don't mind, as you have a question, just kind of jot that down, and we won't interrupt the session. We'll go ahead and get through the presentation. And then at the end, if I haven't gone back and covered the information to answer your question, we'll do some Q&A at the end of the session. So that's kind of how we'll structure this, and we'll go ahead and get started. So the first thing, let's see. All right, so what I want to do is just ask and answer a couple of quick questions. Who's responsible for bonding and grounding? Who's responsible for bonding the network? Well, the answer is the service provider. 100% responsibility lies on the service provider. It's up to us to make sure that the network is bonded and grounded properly. The next question, if a customer disconnects or alters the ground, is the service provider still responsible? The answer to that is yes. We are always responsible no matter what has happened to the ground. As soon as we become aware that there's a problem, we need to do what is necessary to get it corrected. Okay. So next question, are network speeds getting slower? Of course not. Are network bandwidths getting lower? The answer to that as well is no. MSOs are going to continue to step on the gas pedal, plow forward, ever increasing speeds, bandwidths, data rates, etc. That's just it's always been that way, and it probably always will be. So some of the little problems that become big problems, especially at high data rates, poor connector prep is a problem, violating bin radiuses on cables, and also poor bonding and grounding. They create problems when that happens, and they're just speed killers. So, you know, everyone does the big things well, but it's the little things that are really going to tighten up your network and actually allow you to take your network to the next level. Fewer problems, not only for you as a technician, but also for our customers. And that's absolutely what everyone wants. So today, what we want to accomplish, we want to provide information on bonding and grounding and go into some detail to clearly explain the difference between what is a bond and what is a ground. Okay, we want to understand why the bonding and grounding is important. Some of that we've already discussed, but we'll go into some more detail on that. I think one very important item that we'll discuss is understanding the bonding hierarchy, the batting order of what are the preferred methods of bonding and locations to bond and particular material to use when bonding. Another thing we'll discuss that there's a lot to understand around the challenges of using ground rods. Plenty more detail on that as we get into the presentation. And then we also want to do a quick review of some of the products that are available and the proper application and use of those products. So understanding all of that, it'll certainly help you understand how to do your job better. All right. So getting into the grounding and defining what grounding is, a ground, okay, there's a large conducting body, which is the earth. It's used as a common return for an electrical circuit to zero voltage potential. So we send things to ground, to the earth, to zero potential. And we want to maintain zero potential difference throughout our networks. All right. So the earth is the ground. Grounding is an electrical connection with the ground. Okay. A conducting connection between an electrical circuit and the ground. So in the illustration there, it shows a ground rod. The ground rods are 8 feet long, and they're typically copper-clad steel is typically what they're made out of, but their intention is the pathway for the electrical current to go to ground. We'll get into some detail about how the ground rods are to be installed and who can install them coming soon. Okay. For the grounding portion, the targeted resistance from our ground to the ground is 25 ohms maximum. We want very low resistance getting to the ground, okay? If you determine that the particular ground rod that you're using, the resistance is higher than 25 ohms, then that means another ground rod. There's an issue, obviously, with the first one. For whatever reason, whether it's the material that the ground rod was driven into, or possibly someone has altered the length of the ground rod and it's not as deep as it should be, therefore the resistance is higher. So understanding what possibly is wrong with the first ground rod is important, but in any case, if the resistance is higher than 25 ohms, then a second ground rod will need to be installed. The second ground rod will need to be a minimum of 6 feet away from the original ground rod, and they need to be tied together with a number 6 solid copper wire. That's to make sure there is no potential difference between the two ground rods. So everything's the same, zero potential difference. That's something you'll hear a lot. Okay. And the bottom bullet on this slide, you need to be a licensed electrician to drive a ground rod. That's part of the NEC, the National Electric Code. We'll discuss a little bit more about that soon, but keeping in mind, in order to drive a ground rod, you need to be a licensed electrician. So bonding defined, okay? I'll get into some of the detail of this slide, but essentially, to cut to the chase, grounding is when you are attaching to either the ground rod here or the number 6 that runs from the ground rod to whatever the first service panel is at the customer or business premise. Attaching to those is grounding. Everything else is bonding, okay? That's just a general description of the difference between the two. Now, as you can see, there is a lot of metal work from the power company weatherhead to the metallic conduit mast. We've got a meter box, more metallic conduit, and then a service panel. So these metal components, they're not intended to carry current and voltage, but there are times when, for whatever reason, those can become energized. So this is why we want to make sure that we're bonding to give this current a path to ground. Okay. So there's a list of items here on why we ground. A couple that really stand out. The first one obviously is personal safety. And that's the personal safety not only of you, the technician, working around this equipment, but it's also personal safety for the general public. We certainly don't want customers touching energized metal objects on their home and having a bad result with that. And the bottom one, the potential difference, the zero potential difference, that's something we absolutely need to make sure that we're maintaining, okay? So as we go through, you know, why ground protection from high voltages such as lightning, power faults, could be anything from losing a neutral to something with the power distribution system. I'm sure you guys have all experienced power lines falling on communication lines. That causes things to be energized that would not normally be. So we want to make sure we have a solid ground for that. Compliance, that keeps us in compliance with the National Electric Code. Protection of electronic equipment. That includes equipment that amplifiers, line items for the company, but also electronic equipment in the customer home. Okay, we ground so we can dissipate electrostatic charges. I'm sure you guys are aware that, for example, a barbed wire fence underneath the transmission line can become energized just from electrostatic charges. So depending on the atmosphere, that's something of concern. So that's another reason we ground. And then of course, the big one that helps clean up our plant, reduces noise and interference on our networks. So a lot of solid reasons there why we ground, but again, the personal safety and the zero potential reference, very important. So this picture sort of speaks for itself. This is a bad result, but sadly it can get much worse than this, much worse. This next picture, I'm sure everyone has probably seen something similar to this. It's been in the business any amount of time. I'm sure folks have actually touched something that was hot that shouldn't be. You felt an electric charge. If you're lucky, it was low and it didn't hurt you. But that just shows you that it can be anywhere. You have to be aware and paying attention and make sure that you're using your proper safety equipment, foreign voltage detectors, digital multimeters, current detectors. You want to avoid contact with stray voltage at all times. So now we're going to look at a bad example of bonding. What we've got here, you can see on the left side of the screen, we've got the power company system and their ground rod running into the house, and obviously the customer equipment plugs into that AC. On the other side of the home, we've got the cable TV drop coming in, and it is tied into a separate ground rod. Okay. The reason this is bad is because there is not a number 6 bare copper tied between the two ground rods so that there is zero potential difference. So what is almost guaranteed is the resistance on the power company ground rod differs from the cable TV ground rod that has been driven. And that difference may not be a lot, but if one of them is 20 ohms and the other one is 10 ohms, then obviously electricity follows the path of what? Least resistance. So the current is going to flow to the lowest resistance point, but the issue is in the event of, say, a power surge or a lightning strike, as that high current event is occurring, the voltage dissipation, while that's occurring, the resistance is going to change between the two ground rods, okay? So that voltage is going to be looking for the lowest resistance path to ground, and that's going to be alternating between the two. So as that current alternates between the two, what's in the middle? All of that equipment that's tied in the middle is going to be taking surges because it's not all same potential to ground. And you're going to end up with a lot of fried equipment in the customer home. And that's where we start taking calls from customers looking to have TV sets and microwaves and everything else in the house replaced because of the way the grounding was installed on the home. At that point, we don't have a lot to defend ourselves with. So let's look at a good example. So, let me back up and mention one other thing. Typically what I've seen in the past in this bad example where we end up with two separate ground rods, we will see for whatever reason, the system design, the plant design does not provide a good route to allow the customer drop to hit at the same location where power hits. In other words, power on one side of the house and then cable TV on the other side. If that's the case, you know, it's one of two things. You either drive another ground rod and run a number 6 between them, which sort of is a very difficult thing to do, or you have to take the drop and you basically either have to wrap the house around the outside of the house, go through the attic, or go under the house in order to bring the grounding point to the same location as power. So that's just one example I wanted to mention what happens if you can find a way to reroute the drop to where power enters the home. It just makes things a lot simpler and there's less chance of this particular situation happening. Okay, so now the good example. Now we've got everything going to the same ground rod, obviously, which is what we want to see. Now it meets NEC, the National Electric Code compliance, and there's zero potential. It's a safe, properly bonded home, which is what we want to see. So another way to look at that is this simple example. It's got all the communications providers. Obviously, either the home or the business is the protected facility. Everything coming in is bonded to the same ground rod, zero potential difference. This is the situation we want to see. Okay. So this device, I'm sure most of you are familiar with. If not, this is what we call a ground block or a bond block. It's where we connect the coaxial cable and run our ground wire to whichever connection point which is the best option for the install. So the National Electric Code states that obviously you need a quality ground block, but it also that all work at the premise must be done in a professional and workmanlike manner. So you see on this ground block, there's 2 mounting holes. That implies 2 attachment points, and there needs to be 2 screws in the ground block. Could you put 1 screw and would it stay up? Yes, it would, but that's not what is considered professional quality workmanship. 2 holes indicates 2 screws. You could all put your family in a car and run them down the highway at 70 miles an hour with only half the lug nuts on all the wheels, but I don't think anybody would do that with their loved ones. So let's not do that with our customers and do a halfway install. 2 holes, 2 screws, securely fastened. You've done some quality workmanship. Okay. So now we're going to look at some bonding and grounding options. This is some of the equipment that obviously we can use. We just looked at the bond or ground block here. We've got a couple of clamps here shown that can be used on the meter box. One of them's a side clamp, one's a front clamp. We've got metallic conduit here where we have ground straps. Okay. Back up to the meter box. We've also got some strapping that can be on the side of the box for a proper electrical connection. Moving down on the power company ground wire, this is the number 6. We've got some bronze vice clamps. And then for the ground rod, we have bronze ground clamps and also this type clamp here, which is also approved for water pipe. So ground rod or water pipe for this particular device. And the beauty of these devices is that they can be installed with a single tool, which is the can wrench. 7/16 on one end, 3/8 on the other. It'll operate everything to tighten and use these devices. So that's a handy thing that you can install them and tighten everything with a single tool. So here's another look at some available components. Again, the bronze vice clamps, they're engineered in a way. Well, let me just talk a little bit about split bolts. I'm sure many of you have used split bolts. They are absolutely a viable option. The one thing you'll notice about the split bolts, they have a fairly large nut that you use to tighten down on the device. And with the large nut, they have large threads. And the issue with the large threads is you can do a fair job of getting these split bolts tight, but the problem is that as we get big temperature swings from hot to cold, that expansion and contraction of the metal, split bolts are notorious for loosening up. The vice clamps are built with a much tighter tolerance. The bolts in those, rather than having a coarse thread, they have a very fine thread. So you can, when you tighten down on those fine thread devices, the way they're engineered tightly, when you tighten them, they stay tight. Okay. So I want to discuss the bonding hierarchy or the preferred batting order for how to attach a ground. Every MSO may not be exactly the same, but this hierarchy list is going to be, it's going to be pretty good for almost everyone. So the number 1 on the list is the IBT. It's an inter-system bonding terminal. I'll go into some detail on that later in the presentation. That's something that you would not be installing, and I'll talk more about that, but it's either there or it's not. So moving down, the number 2 option there would be the power ground wire, which again is the number 6 that leaves the ground rod and goes to the first service box on the home. Number 3 option is the ground rod itself. We'll discuss challenges using that. The metallic service mass conduit. And I want to be careful here where we're talking about attaching to the mast. We're talking about installing a ground strap, not attaching a drop to a metallic service mass conduit. All right. Next one on the list is the power meter box. We have lots of options for that. We'll go into detail with it for attaching to that. And then the last option on the list would be a grounded interior cold water pipe. Okay. And I'll talk some more about that with an illustration within 5 feet of the water main entry. Again, the 25 ohm max resistance. And then one other bullet I want to mention is we never want to bond to an external water pipe, a faucet sticking out on a wall such as that. That is not a good bonding point. Okay. So I know you won't memorize the batting order yet, probably, but as we look at this illustration, we're going to skip number 1 for now, which was the IBT. The number 2 option on the list was the power ground wire. So that's this number 6 copper that goes to the house. That would be option number 2. All right. Option number 3 would be attaching the ground rod to the ground rod with our ground wire. Okay. Option number 4 would be the metallic conduit with a grounding strap. And let me just mention real quickly, it probably goes without saying, but I'm going to say it. Make sure that this conduit is metallic. We have seen technicians attach ground straps to PVC conduit, and PVC is not the best conductor, as you can all imagine. So again, metallic service mast conduit. Okay. Next option on the list, number 5, is the meter box. So we've got several examples here. This particular example is a side meter box clamp. There are instances, obviously, where the meter box is mounted flush to the wall and you can't get to the sides. So there are options for front meter box clamps. And then also there are straps that can be attached to the meter box. Okay. And then lastly, the cold water pipe. So in the illustration, it shows option 1. This is the input line from the street. If you can get to this within 5 feet of the water main entry into the building, and you attach at this point, you're good. You ground to that clamp, and you're good. Now, option number 2, if you can't get to this point on the input side, you can bond to the water pipe on this side of the meter, on the home side of the meter. But if you use this option, then you have to install another clamp with another ground wire that loops past the meter. Reason being, occasionally meters get replaced. If the meter gets replaced and we don't have this strap in place, then obviously we've just lost our ground, and that could create a very dangerous situation. So if you have to bond to this side of the water pipe, make sure that you have this jumper installed in the event that the water meter gets replaced. If there will be some situations where none of those options are available, contact your supervisor. You're going to need to get help at that point to come up with a solution, but a solution needs to be found. It needs to be done. So be sure to get with your supervisor in the event none of the options are available to you. Okay. All right, now we're going to talk about challenges attaching to the ground rod. Okay, so the first thing is, according to the National Electric Code, the ground rod is supposed to be driven completely into the ground where you can't even see it. Now, I know that that's not always the case. There's often a few inches of ground rod sticking up out of the ground where you can see the clamp. You can actually see where the number 6 leaves the ground rod, so on and so forth. But here are the challenges. When attaching to the ground rod, you never want to touch the ground rod with bare skin, with bare-handed, because if you touch the ground rod, you become the ground. That can be very dangerous. So that's the first challenge. So now you're working with hot gloves if you need to touch it. All right. So your clamp or your connection cannot abut against another connector on the ground rod. Okay. So you can't, there's got to be some space between the two on the ground rod. If that room is not available, then that takes that out as an option. All right. Your clamp or connection cannot be on the very top end of the ground rod. There has to be some portion of the ground rod sticking through the clamp. All right. You cannot dig down, take the dirt away to move something to free up space on the ground rod for your connector. That is not allowed. You can't do it. Okay. The next one on the list, as we've already discussed, in order to drive a ground rod, you need to be a licensed electrician. you got to have a permit to do electrical work. So for all those reasons, attaching to the ground rod is a challenge, to say the least, and generally not recommended. Okay. So here we're going to look at some options for ground straps. On the left, I want to mention this is a hook and hole device. The hook being here, and then obviously different holes depending on the size of the pipe you're attaching it to. I know many of the clamps out there, you actually have to take the bolt completely out and run the bolt, try to pick the right hole, run the bolt through the hole, tighten it up. If you didn't pick the right hole, you got to take it apart again, go to the next hole until you get it right. All right. This particular device, again, a hook and hole, you put it around the conduit, the strap, the pipe. All right. Pull it up as tight as you can, hook it, and then tighten down to tighten it up. Again, with your can wrench. And then you use this nut here with the other end of the can wrench to tighten up the clamp on your ground wire. Okay. Over here is same device basically, but it's copper on a copper pipe. I do want to mention, if you've got a galvanized metallic conduit, use a galvanized strap. If you've got a copper pipe, use a copper strap. Don't use copper on galvanized. Don't use galvanized on copper. You don't want the dissimilar metals. It's going to deteriorate. We're going to have electrolysis. It's going to corrode. And before long, you're no longer going to have a bond and you're going to have problems. Most likely, you won't know about it until you get a call from the customer, which is bad news. So we don't want that. So use the proper device in the proper situation. Okay. All right. So I want to go into some detail here on these meter box clamps. Not all meter box clamps are the same. I'm sure some of you guys have used some, and gals have used some clamps that basically when you tighten them down, they don't stay where you put them. They kind of walk as you tighten the bolt down. With these particular devices, you don't get that. If you'll look in this section here, there's a center point in the bolt that tightens down. And if you look on this illustration, it's kind of hard to see, but you can see the center point is the first thing that touches the meter box. And then the 90-degree design of the clamp comes down, and then this clamp lock, it doesn't try to pry the meter box apart as you tighten it. The pressure down here and the pressure up here is a flat pressure, not a prying pressure, if you understand what I'm saying. There's not a big hook that's going to pull this strap away from the meter box. And then the next thing is these teeth in the bolt, they do a really good job of grinding through the paint or the powder coat on the box so that you get a very solid electrical connection. And then the other thing I want to mention about these clamps is, just like the bronze vices I talked about earlier, these things are engineered with very fine threads. You can put this device on a meter box, and actually you can start to just hand tighten it with your fingers, and you can feel the way it's machined. It's a quality device, and you can actually get it to bite into the meter box just with finger pressure. So not all devices are built the same. Something quality like this, it's quick, it's easy, and it does a really good job of giving you a solid electrical connection. Okay. So here's something we talked about earlier. There are times when the meter base is flush against the wall. If that's the case, then we have front mount clamps to be used on the meter box. So that's just another option if you end up with some flush mounted meter boxes. Okay, let's talk a little bit about ground wiring. So you want you want to run your ground wire, you want it to be as short as possible, and you don't want any sharp bends in it. You want to use gentle curves. All right. The length of the ground wire, first of all, it cannot exceed 20 feet. All right, 20 feet of ground wire. And it could possibly be required to be shorter than that. So, you know, overall, the maximum is 20 feet on a ground wire, but if you've got a really short, it has to be no longer than half the distance of the shortest outlet. So if you happen to have an outlet that drops right in, goes through the wall, and is only 15 feet long from the splitter or the ground block into the home, if it's only 15 feet long, then your ground wire can only be 7.5 feet long, half the distance of the shortest outlet. Now, if all of your outlets are 40 feet long or more, then obviously we're using our 20-foot maximum. All right. So the NEC says the minimum size ground wire, and these will all be solid copper ground wire, for RG6 is number 12 gauge. That's American wire gauge. Number 12 for grounding RG6. This slide, that's a typo. I'm sorry, the next one's got a typo. When the distance of the ground blocks to the main ground is further than 20 feet, then a number 6 is required. But here's the issue, everyone. If you think you want to run a ground wire longer than 20 feet and you have to use a number 6 solid copper wire, first of all, no customer is going to want that on their home. And secondly, just think of how difficult it's going to be to neaten up a number 6 solid copper ground wire and make it look like anything. So for all intents and purposes, you can basically write off using a number 6 ground wire on a home. Okay. Here's where the typo existed. Again, number 12 for RG6. This shows number 6 for RG11, but that should actually say number 10 American wire gauge for RG11. So just so everyone knows, not every MSO, but a lot of the major MSOs only stock number 10 gauge ground wire. That way, any drop wire that's installed, they're covered. So, but just keep in mind, number 12, if you're RG6 minimum, number 10, if you're using up to RG11 coax. All right. And again, the ground wire shall not exceed number 6 in any case, which again, we've pretty much written number 6 off for installation on the side of the house. Also, the ground wire on the jacket will have labeled what gauge wire it is. So it's easy to identify what type of ground wire it is you're using. All right, so getting back to the IBT, the code, the NEC National Electric Code requires that you use the IBT to ground to if one exists on the home. So they're quick, they're easy. Let's see. This is an illustration of the single bonding point for for example, the IBT. We've got the power company that is direct, and then all the rest of the providers, cable TV, telephone, internet service providers, all go through the same device. And this is an IBT. You basically, it's got a plastic lid on it. You push the clamp, open the lid, you put your ground wire under the lug, and I think these things are actually labeled. So, but in any case, it doesn't matter which one you enter as long as all the providers are common with this IBT. So you can bond ground wires from multiple communication systems into a single main ground. And again, this device will either be on the home or it's not. I think this change went into effect more than 10 years ago. I think it was 2012 when the code required that all new home construction have this IBT installed. So I know not all homes were built to code, but that's what it says. If that is there, just use it. It's easy and you're good. Okay. All right. So drop disconnects. I'm sure many of you have disconnected drops before and seen a spark. This is something where if you need to disconnect a drop, particularly the input side of the drop from the ground block, be sure you're using your foreign voltage detector. You want to avoid disconnecting these as you can, if you can, but we know, that at times it just has to happen. So there could be voltage on the sheath, voltage on the connector when you touch it, and when you pull it apart, you could get a nasty shock. So be sure if you have to disconnect it, you're using foreign voltage detector and protecting yourself at all times. Okay. So now what I want to do is show you some examples of handiwork that that there's basically some issues with. So here we've got an example. This is what I was talking about, a device that would actually pry the side of the lip of the base, the meter base apart. That's not a good situation. It's damaged the box. Also in this particular install, the bolt that should be screwed down to the box is not even touching. So essentially we probably don't have a solid bond here. So that one's going to be an issue. Okay. First of all, with this one, I can't really tell if that's a copper pipe, but clearly they've used a copper ground strap. The paint is not a good conductor. Obviously, the paint should have been scraped away, and proper ground strap should have been used. So depending on what kind of pipe that is, there might be a couple of major issues with this particular installation. Okay, so here we've got a ground rod that someone has used a power strap on. So again, not ideal and probably not a good solid ground. Another one, we've some discussion about whether this box is metallic or plastic. Even if it is metallic, that is not where a clamp should be installed. Certainly going to interfere with the opening and closing of the lid, but that's where the technician decided to go with this one. Okay, this is a good one. Install was completed, but no ground was installed. The technician did leave a note that they were going to return at a later date to install the ground. Really, the only thing missing here is they should have added good luck to the message for anyone that comes in contact with anything on this home. So not a good one. All right. So as we attach to these meter boxes, one thing that we've got to be sure of is that we're not impeding the power company's ability to open the box and either work on or replace the meter. Clearly, this particular strap was not installed in a way that would not impede the power company. The power company is not going to be happy with this. They don't want to have to take anything off to be able to access their equipment. This is going to endanger your relationship with the local power company. It's just something we don't want to do. So improper installation, it's a good strap, it's just not in the right place. So keep that in mind. Okay, here's one that ground wire is just installed on a screw on the plate on top of the meter base. Certainly not a good connection. Here's another one, ground wire under a screw, heavily painted, not to code. Another example of the same thing. And here's one of the water pipe examples that looks like someone used a radiator hose clamp on a ground wire on an outside faucet. Again, not a solid connection. Okay, so here we've got a galvanized ground strap installed on a galvanized pipe. However, that's a handrail. That's not a conduit, electrical conduit in any way. Handrails are not good attachment points. I'll just leave it at that. Here's another effort. Got to give them credit for trying. It's just not effective. And here's one that if I didn't mention earlier, I probably should have, but we never, ever want to put a ground strap on gas pipes. Gas pipes are not an option. It's dangerous. It's not to code, but here's an example of that happening. So no ground straps on gas pipes. And with that, thank you for joining. Jason, do we have any questions?
Well, first of all, Frank, thanks a lot. You did a great job going over that. I really enjoyed the pictures and stuff too with the examples. I know I personally learned a lot, so thanks.
Good deal.
I don't see any questions in chat, but if anyone on
Jason, I see one question in the question module. If the copper AWG6 is bonded to the power meter, why is it considered grounding instead of bonding when you put a split bolt on it?
Trying to understand that question. For all intents and purposes, the definition of grounding and bonding, it's really about location. That's all it is. It's all the same. It's an electrical connection. They're all connected together. It's just the terminology is that the ground rod or the number 6 from the ground rod to the first mast is our first service box is considered grounding, where everything else is considered bonding, or that's the term used on it. It's purely about location. They're all common.
All right, thanks, Frank. And do see one other question. How big of a risk are ground loops?
How big of a risk are ground loops? Not sure I'm understanding. Are we talking about, whoever's asking the question, are we talking about installing a loop in the ground wire?
Hey, Brian, I don't know if you're on. Do you want to expand on that, on your question?
You may have to unmute him in the attendee list.
All right, Brian, I just unmuted you. You want to ask?
Yeah, just ground loop, just difference in electrical potential for grounds. You kind of touched on it a bit, but I wasn't sure how common that was, I guess.
Well, just generally speaking, we don't want anything that's in the electrical circuit, any of the conducting devices, we don't want any potential difference. So that's why, you know, for example, the dual ground rods, that's why, you know, they absolutely have to be tied together with number 6 copper and all of it buried so that there is zero potential difference. So anything we're dealing with, we want zero potential difference from say the vertical ground on the pole, the strand plant, you know, we want all that bonded to ground. Same, basically the same thing at the home. Even though it's all tied together, we want everything with as solid a ground as possible so that the minuscule potential difference is almost nil. We don't want any path of electricity finding a lower resistance path to ground. For example, when the human body touches the metal, we don't want the human body to become the lowest path of resistance and current flowing through a human. We want it going to that ground rod. And I'm not sure on the term loop. Again, any ground wire we install, we want gentle bends, no 90 degrees. High current does not like to make turns. It tends to blow out. So any turns or loops or curves that need to go into the ground wire, we need to keep them as gentle as possible and keep the ground wire as straight as possible. Okay.
All right. Thanks, Frank. Any other questions? Nope, I don't see any else. All right. Thanks a lot, Frank. That was really good.
All right. Thank you, everyone. I appreciate your time this morning.
Yep. All right, Nick, are you ready?
Am I ever? Yes.
All right. I'll do a little introduction for Nick.
Okay.
Nick Segura is Principal Engineer 3 in the Network Technology Group outside plant for Charter Communications. He is responsible for architecting new RF technology solutions in the HFC realm to serve the company's vision 3 to 10 years out. Nick is in his 21st year with Charter, where he owns company standards and specifications and shares recommended practices with leaders to achieve alignment with company goals. He has been active within the SCTE for 31 years and participates in several engineering, interface practice, and network operations committees, and remains an active SCTE proctor. Mentorship and soliciting new talent for our industry are activities at the top of his list. All right, take it away, Nick.
Thank you, guys. And can you hear me okay, just to make sure?
Yep, all good.
Awesome. Thank you so much. Welcome, everybody, and thanks for tuning in. SCTE is the place to be. It's the way to grow your career. I'm all in. Been in for 31 years and just love it. Thank you, Frank, for grounding us on the understanding of bonding. It's like your presentation. I lived it, and everything you said is right on track.
Nick, sorry to interrupt. Can you swap your display settings?
Oh,
swap your monitors.
Thank you. I thought it was swapped. How's that look?
Good, thanks.
Awesome. Okay, thanks. In my presentation, I'd like to just ask you to look into what's happening with high split and extended spectrum, and don't be afraid of it. Lean into it, like many of you seasoned veterans do anytime, anyway. Seek to understand, and it's really just a growing, learning, fun experience. I could tell you there's trials and tribulations, but you're rewarded at the end of the day for understanding how it's going to be implemented and following the guidance and then having feedback, teach to others, and you will be rewarded by knowing more. In this topic, I'm going to share with Monty Preston the high split topic. And Monty, I'm not going to present any of those slides that we talked about. However, I'd love to be in a conversation on questions. So in my topic, I'm going to just define the bandwidth and diplex filter range, what's different about it, a lot of the challenges that I've talked to many about with implementation, the technical HFC operational challenges, some with test equipment, some with just tilt. Tilt happens, and we'll talk about that. Implementation of high split, how do you get there? Adjacent channel interference is something I'm really versed on. I did some testing and recreated the issue, and we'll talk about that. And then just some of the deployment about tools and needs. I will take questions dynamically, so please interrupt as you have them. There we go. I was already there. Oh, here we go. So You're seeing the big circle, right, with maintain legacy spacing? Okay.
Yeah, correct.
Thanks, I was a slide behind. The fortunate thing with high split and 204 is we're not moving past 1.2 yet, right? We're able to maintain this spacing for amplifiers, which is key. I mean, talk about lucky or skilled. Like, I'm going to talk about our new hybrid manufacturing and how we support this higher bandwidth without having to respace. That's a killer advantage to any other competitor. There are minimal changes with values on taps. As we get to 1.8, that's a different story. But we're able to maintain consistent RF levels for current frequencies. And that's been the key, right? Don't change what's been installed in houses for years. We may tell you about a slight reduction in the upstream transmit, but there's no excessive transmit problems because we've known through many out-of-spec installs, we painted ourselves in a corner for max transmit of a modem bonding all carriers. That's not happening here with high split. Just crazy that we can maintain that. We'll talk about more of that, but ensuring that the majority of our actives are able to be swapped out with the existing housing. That's key in charters. It's so big, right? The plant's so large that to maintain housings and those hardline connectors that we know are good, we've been using PNM and other FBC for years. Don't swap out the housing if you don't have to. So we're focused on just module swaps. And then tilts levels back to what's intuitive to a maintenance technician for forward and return levels through the hardline plant. If we can keep it standardized on a standard channel plan, that is key for everybody's simplicity and rollout. That's kind of been our leadership goal, is to keep it simple. Just a quick note on forward power amplifiers and then return. Again, major kudos to our hybrid and gain stage vendors for getting us to successful stages to carry more bandwidth in existing amplifier housings that have to dissipate heat. But these things draw much less power than expected. They're letting us put them in existing housings and having that extra power or total channel power, which is the limiting factor for gain. Here's a quick upstream view of that too, but these new gas-fed gallium arsenide chipsets allow for the increased return bandwidth at higher cable losses at higher frequencies. This is worth 1,000 words. The picture is in the upstream here. Stay into the safe, high dynamic range window. At Charter, we standardize on return input level of 11 dBmV for all amplifiers of all nodes, keeping it simple regardless of the spacing. 11 gets us that 31 from a cable modem at the same port on the output of an amp going backwards. It allows us to have this target of the target NPR of the 5 dB dynamic range. That's greater than 55 dB for all manufacturers. So just to the left side, the blue is the cool blue. You're maintaining above noise region, but don't fool yourself. It's always, in our industry, the carrier to noise and the distortions, you got to find a balance. Blue on the high end would be, have enough level going into that amplifier. Getting into that purple target input range, now you're getting the best carrier to noise with the best distortion. And then if you're gonna go too high, you're gonna get into that zone, the bit error rate crash zone, or the clipping region. It's dominated by those higher order and modulation noises. And it looks a lot like laser clipping, although you will not see that in DAA anymore. It still shows up in the same, error correction, right? In your DOCSIS tools, you'll see your coded errors, correctable, and then uncorrected, and you've clipped. So here's some challenges. So this is just a bandwidth, expansion view. It's quick. operating today at 860 or 750, some 1 gig systems. We're all going to get to this DOCSIS 3.1 dominated world with 1.2. How do we get there? The 4 HDMAs that we've been operating at Charter remain, as long as there's still significant 3.0 modems. There's still quite a few DOCSIS 2.0 modems and set-top boxes that we're gonna continue to maintain. So 4 HDMAs is our start. Then we're gonna expand it with the 8 OFDMAs. I want to get to the next slide to show you that. But look at the potential speed increase. It's 11 times in the upstream. Crazy. And then there's a 95% increase in capacity in the downstream. But how do you get there with all those legacy set-top boxes that are out there? You see that the out-of-band carrier traditional legacy is at 75.25 in Charter, some at 104 in other systems. It's got to be reclaimed. So that is our mantra. We reclaim all legacy non-DSG set-top boxes. They get pulled out for high split conversions, but we can maintain the DSG set-tops as long as we have a handle on what we call adjacent channel interference. And I'll get into that. Take a look at the right side in the lower level. As we get past 1.2, and maybe Monty will talk about this, is total channel power increases so high that we'll have to incur a step down, or we call it a stair step, so that CPE can handle the extra power, so that our amplifiers can handle the extra power. And because of the LDPC error correction in OFDM, we can get there. There's a lot of improved MER, and especially when you go into DAA, this was one of the requirements. You have higher MER, recent MER that you can support this with. And you see a note about MoCA. That is something that you want to begin getting out of. You can support a customer-owned MoCA, but you got to separate the two devices out of the splitter network. And maybe Monty will cover this, but with a DOCSIS 4.0 gateway, that's easy to do because you will have one outlet for the cable company. Connector at the tap, 2 connectors at the phone block, 1 connector at the CPE. You're done. Reclaiming bandwidth to get to high split. This is a view of a pre-high split. So this is a traditional 5 to 42. We'll reclaim all of these SC QAMs between channel 2 and channel 29. So the first SC QAM will be channel 30. And we will start with SC video QAMs company-wide. This is pretty cool. You may be in a small city with only 32 SC video QAMs. You may be in a large city like Los Angeles, California. They've got 42 SC video QAMs. But wherever you're at, we'll stack those from channel 30 on up. And then it starts with DOCSIS SC QAMs. So we are still running 32 downstreams everywhere, all the time. And unless there's an exception, but that's very few and far between. And then you'll see that OFDM starts the first haystack or 192 megahertz block is what begins after the last 32 DOCSIS QAM. Beware of LTE ingress at this point. We know it's there. We have great tools to detect it and to mitigate it. And by the way, on bullet 2, I just want to mention company-wide at Charter, we support the local origination, like add drop, or properties that have their own video channel. 33 is what we chose. And then, of course, we can make modifications or grow as needed. Last comment here is CPD, comment path distortion. It's back with higher downstream bandwidth. Expect that you will have the same compromised tap port or I guess issue with capacitance on a connection, corrosion. But when you have more downstream power from downstream channels, it comes back in the upstream and raises your noise floor, CPD. That didn't go away. It's not the pitchfork like it used to be because analog carriers are gone, but you will see that elevated noise floor. Same correction, Same troubleshooting, but you may see more of it based on downstream loading. And I'm going to mention about leakage and OFDM pilots in a minute. Here's an upstream view of OFDMA and ATDMA coexisting using the return path monitoring tool from Viavi. I just want to note that there is some carrier tilt. If you are viewing it at the end of line, say the customer location, it's natural to see the 5 to 204 tilt now in your meter. Don't fret. You are expected to see flat OFDMA at the amplifier or node location though. So how much tilt can you have? I have a slide about that towards the end, but it does take time to go into dynamic range window. You can have up to 12 dB tilt. That is pretty amazing because in order to exceed that, you would have to have express runs that are over 2,500 feet. Super long drops that weren't meant to be RG6 anyway. This is one of the things that you'll get high visibility to, but if you just keep things within spec, tilt is not your enemy. You'll see FM band. We'll talk about that a little bit. We like to exclude the FM band 88-108 initially, giving ops time to get into houses. But in fact, we're in trials right now with our PMA, profile management application, to use the FM band. Right now we're doing this in Nevada, and we're able to reclaim some of that 88-108 based on the CMTS CM exchange of logic coefficients, code words. Essentially, when there's an FM band carrier that does get in, the CMTS CM negotiate that mini slot or that subcarrier as non-usable, and it will bypass it, 0-bit load it, make it so that it doesn't hurt the whole OFDMA channel. It's very exciting. It's working very well. We're probably going to go to scale before too long, and then we'll focus on downstream PMA. Same kind of effect. Take a look at the 138.8750 OUDP signaling. So today, and for the last 2 years or more, Charter's been configuring CMTSs, whether they're iCMTS or DAA, vCMTS, to command modems to come back 24 hours a day, 7 days a week, to transmit this OUDP signaling. It's 1.6 megahertz wide. We're going to talk about that in a little bit. But from the time you turn it on and just never turns off, you'll see the signaling coming from the CM to the CMTS. And it'll be there so that when there's a leak, crack in the cable, squirrel chew, you will be able to detect that with leakage detectors that we've been purchasing from 3 vendors. So I'm not going to spoil the biggest conversation about OFDMA, but it's bonding, right? There's so many reasons why you may have bonding challenges, and it's levels and it's interference mostly. But take a look at some of the capacity changes when you go from 2-channel OFDMA bond to 1 to 0. You're looking at a huge degradation. Tilt, by the way, is another amplitude-related unbonding scenario. But this is one of the metrics now that we've put into our health tools. Is like it used to be just coders and MER and level, but now it's a status of bonding. You know, are these carriers fully bonded? Because if they're not, a couple of things happen. You lose that capacity to the customer, of course, and back. And you lose, if the right side's unbonded, you lose that OUDP signaling for leakage. No bueno, not good. So as well as when things are going unbonded on OFDMA, guess what? Your ATDMAs are the fallback. If you still have 4, you may have 3 or 2, depending on how many D31 modems are penetrated in your node. But when you lose your OFDMA, all of a sudden you have congestion on those ATDMAs. If you have super users that were used to using OFDMA, and now they're taking away some of that bandwidth from the D30 and D20 modems, and all of a sudden congestion is a real thing. So keeping things bonded, paramount. Next slide. Okay, that was harder than I thought. OFDMA 1 can unbond if you don't have an exception band in your FM. And Charter again is starting to repopulate the 88 to 108. If you have too much FM or PMA is not enabled, that channel will unbond because it's right there in the FM band. It doesn't matter if it's a small city. We determined out in the middle of Oregon, there's enough FM stations that it still wreaked havoc with that carrier. And if you go into big cities, just there's no chance. New York City, there's a FM band station every 200 kilohertz. It's crazy. Let's talk about FCC CFRs, Code of Federal Regulations. So with this OFDMA implementation, it comes with responsibility to continue what you've been doing, and that's complying with 76.6x codes. Here's how we do it again with OUDP. Take a look at the little orange OUDP signaling marker. We saw that in Spectrum View earlier. It's to the right of the aeronautical band. If you didn't notice, 108 to 137 is the aeronautical. That's what we have to protect or keep reporting done on. There's another band, 225 to 400. But this is where we've chosen to put the OUDP signaling from the modem now to the CMTS to begin monitoring. It's only 4 mini-slot wide, 1.6 wide megahertz, and burst with pilot pattern 4. I'm going to show you a slide that it's a little more complicated, actually having to configure your leakage meter with CMTS settings so that the modem matches, the modem transmit burst match the signature requirement of that leakage meter so we can detect the leak. I suspect it's going to be pretty similar across MSOs, whereas the leakage meter manufacturer can keep a standard skew, but really it's a setting inside the meter that you have to get right with the CMTS configuration. Here it is. I just have the OFDMA parameters on the left. It gives you the number of subcarriers and the guard band, and IUC modulation profile. But on the right side is kind of we did an all vendor trial or interop here at the office several years back, maybe 4 years back. And these settings that you see for subcarrier spacing, cyclic prefix, symbols per frame, this is what we've landed on for a standard. It's not secret. It's just how do you get the best detection in the loudest or noisiest environment consistently. So there may be improvements to this at some point, but right now we're pretty proud to say 3 different meter vendors can get this OUDP burst signaling off air when there's a problem with the coax, and they do it consistently and do it well. We have some pretty cool information on a technician using the new OUDP instead of a 138 CW. There's a little more recognition of the tone or the warble changing a little bit slower. You have to be a little more patient. Remember, like, say you have 200 modems that are 3.1 on a node, and every one of them is signaling back OUDP. They're only going to get back 2 or more times per second each. Whereas if you only had 10 modems on that node that were 3.1, remember this is only a 3.1 modem thing, then they would get back more often, maybe 4 to 10 times per second. So your meter is going to at least detect 2 or more pulses from that modem in that premises every second. So you'll hear it, but it won't be like steady. Sometimes it'll be warbly. So patience, we've found that we are getting more leaks. Depends who you talk to. Pretty much premises leakage levels are higher if the modem is transmitting above 40. That's a lot higher than it was going downstream at that frequency. There's a lot. This is a seminar topic in itself, but is it broken? No. Does it bring you to the problem of the coax? Yes. It's kind of like when we launched 612 leakage tag. we got a lot more leaks, but they were tied to double gaskets and taps and different connector issues. This brings you to the same problem, but more of it. Also think about OUDP being the same level as the carrier itself, whereas in the past we're using the CW dual tones that were 30 or 33 dB below carrier. Same accuracy of a leak detection, but you get more dynamic range. The signal's higher, so your chances of getting a more accurate or non-false leak are better. So even the reach to the backyard from the street, again, not more leaks, but maybe because you get clarity, you have more strength from the leak, your meter is able to understand it. A quick note, if you do have downstream 612 and you put OFDM over it, your best bet is to move to OFDM pilots for your signal leakage detection meters. B, you can create a 1 megahertz exclusion zone like we did in one property here, just so that 612 gets through. It's a waste of 1 megahertz. It's not significant. It's an option. It's the second option. Any questions so far? All right. This is a phenomenon that we will experience if you have a customer with a legacy set-top box, DSG of course, in one room or in one house, and then you have a DOCSIS 3.1 or 4.0 modem transmitting, middle to high of its capability, and you will have the upstream energy between 54 and 204 that never was upstream before, kind of get through a two-way splitter, bounce off a tap port, and get into the face or the tuner of the set-top box. What's the cause? Well, the set-top box isn't necessarily seeing spurious noise or babies from these harmonics. In fact, they're not even harmonics. It's just total energy. The set-top box tuner is actually blinded by its ability to lock onto a downstream carrier. Therefore, the AGC circuit in the set-top box kind of goes wonky and it can't lock, so you lose lock on the video that you're trying to decode or demodulate and you get some tiling. It's real. It's expected to happen like less than 10%, much lower if you keep things within spec. That's for inter-premises adjacent channel interference. And guess what? It's only going to happen when there's like a duty cycle or between 10 and 20 megabits per second transmit of that 3140 modem. It's really hard to recreate unless you limit your speed test using a wireless router or something like that. But I'm going to give you an opportunity to look at this image here, and I'll explain more what's happening. This is hard to find how to set that up, but this is a spectrum analyzer looking at the input to a set-top box. You can see that clearly downstream between channel 30 and up to 860 megahertz. But then you see the left side, and that's the energy coming through a splitter that's feeding, the 3.1 modem, or it's bouncing out the tap port. Return loss is bad, like low value taps are a cause of this. But when we figured out when the height of that interfering carrier on the left side is above a level that creates a delta to the downstream carriers, in this case, I think 20.39, that's the start of tiling for this model of set-top box. Not all set-top boxes are as sensitive as this one. In fact, most of the ones we have will start at 30. So picture 30 dB delta or ratio between the top of the interfering carrier and the lower downstream. It's insane that you would even get to that point unless the install is very much out of spec and the CPE is barely hanging on. So again, this cause and effect is not going to happen often, but it can happen neighbor to neighbor. Think of a college kid and think of your parents with a set-top box. high-speed data. And anyway, it's a scenario, right, that could happen. So what do you do about it? You understand it. You kind of look at your set-top boxes for sensitivity. You teach on how this can happen. Low value taps, splitters that have low return loss or just low port-to-port isolation. And you create this tool. So in our DOCSIS tools, we have a place for accounts. When that account has both 3.1 modem and a legacy set-top box, we'll just do a quick math equation for the tech or the customer call rep representative, and they'll get like a risk factor. If you have, say, less than 20 dB CACIR carrier to adjacent channel interference ratio, it's a made-up term, but it makes a lot of sense. But if you're down way below 20, it's going to be no risk. If you get near 20 for the set-top model, it's going to be high risk. If you get to other models of set-top boxes, this is a medium risk. But just be ready to have one of these. We went and purchased some 54 to 214 megahertz band stop filters. They're pretty low cost. Should have them in your back pocket in your bag if you have a scenario where you can't, well, where everything's in spec. Let's start with that. Transmits and receives are within spec, and your noise floor is the right spot. You'll want to put on one of these band stop filters, but you'll need to put it in before any and all of your DSG set tops, some DTAs, OCAP TVs, MoCA, even. Anyway, all that needs to be protected from the 3.1 modem. And this is one way to get there. Or you can just stick the band stop filter on just the devices that are having the issue. So if we have self-install kits going out of the front counter, we'll have a filter with that set top just in case. Nobody likes filters. They get lost, they get misused. It's a necessary evil in this case, some of the times. So attempting to understand it, don't overuse them. It makes a lot of sense to have a solution. And by the way, if you had MoCA in the house still, you would co-locate it with that MoCA filter. It works in the same manner, same way. And there's just a before filter was applied in this case. You get the tiling. It only happens again when there's speeds of that modem between 10 and 20 megabits per second. We call that a duty cycle. Hard to recreate. So customers will see this intermittently if that premises is mostly out of spec. The solution is get it in spec. I kind of just covered the slide by why would you use a filter and where would you use it? And by the way, having a filter at the tap port makes no sense. It kind of stops the whole self-install for DOCSIS 4 modems. Question to the audience. Well, I'm going to leave it hypothetical here. When you have a short drop, low transmit level versus a high drop and higher transmit level, what's going to be the scenario where this problem occurs? And you got to think about the set-top box return level or downstream level. Same thing, short drop, long drop, high isolation, low isolation, high port to port. You're going to find that there's kind of an answer here, but it's really just going to depend on every situation. Do the math between transmit and receive, and try to keep an understanding that low value taps may be the issue if there's low or short drops. I'm going to stop there. This could get complicated, but try to keep it simple by teaching others where this could happen and why. Okay. When did I keep this slide in? How am I doing on time? Looks like, yeah, got just.
You're good. You got another 20-ish minutes or so if you want.
Oh God, I'll take 10. I didn't realize I had this slide in here. Stand by. Let's talk sweep and balance equipment. I don't have the slides. I have a whole deck on this, but a high split 204 system works very well with sweep equipment. We chose some of these devices here on this page. SCU 1800, it's nice that it goes to 1.8 gig downstream, but it also supports 204. Note to self, any upstream monitoring tool you have or upstream sweep, go past 204, right? You need at least 210, maybe further if you're looking for other anomalies that could affect total power. But don't stop at 204. You want to see the noise floor to the right of 204. We have sweep set up for every megahertz or multi-point sweep points. When you've launched high split 204, but haven't yet activated the OFDMAs, it's a nice breathing 2-week period that will turn on these sweep transceivers, and you'll get a nice view, very granular, very quick rendering of the upstream path. So you could see what you wouldn't have seen when those downstream channels were there. So this is only in an ICMTS market where the head-ends and hubs still have CMTSs. These SCU 1800s work real well. Also that HCU 204 works very well. I wish they would have named it 210 because again, you want to see the noise floor to the right of that. But this is to support high split 204 markets. DAA, quick note, we do have it working quite well with all of our RPD vendors and node housings at Charter. We have a solution of Expert Track Cloud, like normal, with an RCI instance. It's an intermediate server that collects all the RPD return path information and feeds it up to the Expert Track server. There's an activated NDF in the downstream. When the meter sees it, it throws out the return path carrier and call it NDR for the RPD throughput. And again, it is working quite well. We had some early issues, but we've worked through them, and I'm happy to take questions on that later. Stealing Mario's slide, perhaps. This is just a known fact that if you start getting the 1.8 gig taps, you know, the seizure screw contact is a thing of the past. So just understand that there are probes for technicians to use for like ingress detection or a quick litmus test without interrupting service that I want to stick this KS 5/8 inch 24 probe into the side of a tap, but it's not going to work like an I-stop probe, right? That's made for a distance to the tap screw, seizure screw. These new taps have more of a, I guess, the Chinese finger thing. It's not a seizure screw, but you have to get a probe that matches this set inside there. And that's just a demonstration for that. Also know for you ONX users, as you get to higher bandwidth in the downstream, and you're a tech that uses the Ingress Expert feature that is on the left side, port 2, just understand that you may get these artifacts. In the screen on the meter, it's not real. We call it the artifact, but it's related to having such high downstream signal power. And these meters aren't handling it well on the FFT process called Ingress Expert. Again, port 2 is looking at anything, there's no filter. So if you put too much downstream signal in there, say the text at an amplifier or a node, you get these artifacts unless you put on a low pass filter. Low pass filter could be anything that blocks downstream at 210, at 400, at 600. Just block the majority of the downstream signal and your upstream port analysis will be healthy. I do have more. I'm going to stop here. I think questions and answers might really be advantageous after we get to Monty's slide. Any questions right now?
I don't see any questions, just someone asking if they can get the slides afterwards. It said great presentation.
Cool.
If anyone non has a question, you can just come off of
Yeah, I do. Just clarification. So Charter, you guys, Charter Spectrum, you guys are doing both high split and both RPD and analog nodes, correct? I take it you are because you're talking about.
Yes, we started early without RPDs. We did. Yep. That's we're going to round the corner, right? We're only going to buy a DAA going forward when we get to that point. But today we're deploying both. CMTS is still converting those to high split. But mainly the drive is to go to DAA so that we can get 1 at 8. It just
okay. Second question: how long have you been service enabled? Approximately high split. I think you're a little ahead of us on the service enablement and high split.
30 years.
Well, service enabling your high split plant with OFDMA, additional OFDMA carriers. Are you guys down the road on that a little bit?
So yeah, we have dozens of systems, right? So it requires all amplifiers to be changed and the node and the CMTS augmented. But so we've been doing this for more than 2 years. OFDMA again was turned on after you have a settling period when you change all the amplifiers and you reclaim all the video for set-top box video. There's a process.
Yep.
Yeah, it's turned on and we have it running many places.
Yep. Perfect. Thank you. Great presentation, by the way.
Thanks. There's a lot more, right? But I think Mario's going to catch it and do most of the other stuff.
Nick, I do have a question for you. So I know there's a lot of debate in our industry, full duplex versus extended spectrum. Curious, I know obviously the direction Charter's going as well as Cox, but I'm just curious what your perspective is on that.
Oh, FDD, extended spectrum, I think is the route that makes the most sense for keeping it simple. FDX is a viable solution. We do reserve the right to say it could be a tool used in our tool belt at some point. I got to stop there.
All right, thanks.
Yeah.
Anyone else have any other questions?
I'll be ready in case there's something later. And Mario, I'm going to go off video.
All right. Thanks a lot, Nick. Great presentation. All right. So let me read a quick bio for you, Mario.
Yep.
All right. So next we're going to have Mario Amato with Cox. So Mario is an industry veteran with 38 years working for multiple MSOs, contract firms, as well as amplifier vendors. Mario has 19 years with Cox and is currently a principal within the outside plant construction and engineering department. All right, go ahead, Mario.
Yep. Can you guys see my presentation?
Yeah, just swap the display.
You swap display. Okay. How about that?
Yep, looks good.
Okay. Hey, thanks, Jason. Good morning. Good morning. Yeah. Hey, first off, I'd like to thank Frank and Nick for their presentations. Frank, I love the getting back to basics with grounding. That was a great presentation. I think a lot of times that's overlooked, grounding and bonding, but it's so important. And I know a lot of issues sometimes come back to that at the customer's home, even out in the plant. Can cause a lot of issues, up to including response issues inside electronics and stuff. So it's always good to keep that, on your mind. So that was a great presentation. Nick, as always, thanks for being a partner to the SCTE Chattahoochee chapter. It's funny because Nick and I, talked about we were going to tag team this high split, presentation, talk about challenges stuff, but we never really synced up on our presentation. So yesterday, I think when we ran through our run through, we got the first glimpse to see our presentations, and of course, they actually complement each other. They touch a little bit as you would expect they would, but I think with what he presented and what I'm going to present, you're going to get a really good view of what's going on around high split and beyond. Because I'm going to talk a little bit about what we're doing with high split, maybe go a little bit off topic and talk about what we're using high split and how we're preparing our network for the future. So without further delay, I'll move on if I get this thing to work. So spectrum growth overview, right? And I think and Nick had a slide on this as well. But you look at your capacities and subsplit, 106, maybe 120 megahertz, megabits per second capacity, depending on the number of upstream channels. At Cox, we typically, in our subsplit, we could run 4 ATDMA 6.4s, and we actually had a 1.6 down there for our DSG set tops, and I think we can cram in another 3.2 for a fifth upstream carrier that came in quite handy during COVID. It was a good lever to pull. In mid-split, 80 megahertz of usable bandwidth, capacity roughly 350 megabits per second. We are doing that with a 45 megahertz wide OFDMA carrier in the from 40 to 85 megahertz. And then our high split plans, 199 megahertz of usable bandwidth, 1.2, maybe 1.3, whatever that math works out to. By adding a second OFDMA carrier, we are currently excluding the FM band. I know that PMA is coming for us as well, and so that's opportunity probably later. We'll talk a little bit more about our channel bands that we're using here at Cox, and that's why I kind of asked Nick how long. I think we are now just starting now. We've done trials a year ago with high split and full nodes and node zeros and things of that nature, and a lot of testing. But now we're starting to roll that out and actually doing a lot of service enablements now. So I think Charter might be a little ahead of us on some of those deployments, but I think we're all on the same page as far as MSOs go. We know what our challenges are going to be, and all the things he talked about. I know our folks, and us here at Cox, we're talking about the same thing. One of the things that we're doing is with our high split is we're preparing ourselves for the next step, which is the extended spectrum DOCSIS. Can't speak this morning, sorry. Going out to 1.8 gigahertz in our network. So some of the work that we're doing today is actually setting us up, and I'll show you for the next step, and we're going to do it in a couple steps. So why mid-split? What are some of the implications, right? Some of these slides, some folks at Cox might recognize for some of the presentations that we've done, and thank you for these slides. Some folks I got these from. Speed tiers. We are currently doing high split for our RDOF requirements. For RDOF stands for Rural Digital Opportunity Fund. We were getting government assistance to build to underserved areas, and as part of that rule, you must offer at least a 1 gig by 500 service. I believe we can offer 2 gig downstream in most of our nodes today. I'll talk a little bit more about that later as well, as far as bandwidth goes. But in order to offer that 500 megabits upstream, you must do high split, right? When you start to add capacity management, going from sub split to mid split to high split, you're extending the node, the lifetimes of your node, kicking that can down the road. I think we can get somewhere around 10 years or more, with the high split. One of the things that we're doing, and I'll talk about, is we are actually deploying 1.8 gigahertz amplifiers to support, our next step to DOCSIS 4.0. So we're putting in these smart amplifiers. We can auto align them. I'll talk a little bit about that. We're going to be able to get performance data. We're looking at transponders to be able to control these amplifiers remotely. Have the ability to not only link your nodes for ingress suppression, but actually ingress mitigation and troubleshooting, but to be able to go out and extend that out into the RF net, the amplifier portion of the HFC network is a big deal, right? Today, we have to go out and go find where the ingress is coming from a node, and then we have to go, basically, amp to trace down to get down to that last, active device and, then start going tap to tap to tap to find that ingress in most cases. When the ingress is coming from the customer prem, think about the ability to sit in your truck and figure out, what leg and get that down to the last device and say, I need to go to this line extender and my problem is coming from there. The potential troubleshooting savings that's going to occur. So, we're looking at some of that as well. Another thing that putting these amps into is they set us up for, being able to go to DOCSIS 4.0. And I got a slide on that, so I'll kind of wait and talk about that. I'll talk a little bit about single outlet homes. I think Nick touched on that just a little bit as well. It's not something that has to be done with high split. It's kind of something we're doing, in conjunction with starting to migrate. And I got a slide on that. I'll talk a little bit about that. Hopefully eliminating some of that adjacent channel interference or customer interference that Nick talked about. Converting these homes to all IPTV, and that prepares the home for future DOCSIS 4.0, because we believe that when you go to a DOCSIS 4.0 extended spectrum DOCSIS to 1.8 gig, you will need to be a single outlet home, right? Either a gateway or one device in the home. So we're kind of mixing these things together and kind of going down that path, and I know Nick, that was great information about the signal leakage detection. For us, we've outfitted all of our vehicles are outfitted with equipment capable of doing the OUDP. I don't think we've quite deployed that yet, and we'll talk a little bit more about that. Right now we're kind of avoiding that aeronautical band is our plan. What I'm going to talk about a lot here, and which I think is a good complement to what Nick talked about, is the challenges that we are going to have with ingress. And I know a lot of folks on this call probably live and breathe that every single day. So we'll get to that in a bit. So our approach, very high level. First of all, little naming convention for our non-Cox folks. You're going to see this term MTC show up a lot. For us, that stands for Master Telecommunications Center. You might also see a acronym STC for Secondary Telecommunications Center, or a head end or a hub, just so you know. Today, we feed, one of the things that we're doing, and that's why I made sure I asked Nick, that we're doing a little bit differently from Charter, is all of our high split, all of that is being done, and our mid split for that matter, is all being done via RPD. We're not doing that on legacy analog nodes. We're kind of migrating away from the analog nodes. All of this stuff is definitely RPD. So our current mid-split DOCSIS 3.1 nodes, they have 1.2 amplifiers in there. We have 1 gigahertz taps and mixture of DOCSIS 3.0 and 3.1 CPE in the field. What we're doing in parallel for 1.8 is we're upgrading that node to a high split module. Current nodes that we have, we're upgrading them to be able to support 5 to 204 megahertz upstream, and then we are installing 1.8 gigahertz amplifiers. At this point, we're not touching the taps in the field. That will be a second step that we will take to getting to DOCSIS 4.0 when that's ready. So kind of taking this in kind of steps, right? And then eventually we would end up with a DOCSIS 4.0 node, 1.8 gigahertz amplifiers and 2 gig taps with both DOCSIS 4.0 and 3.1 CPE. Our approach with some leveling and a lot of things that Nick talked about was, we're looking at maintaining legacy levels. And as I know Charter is doing, right, maintaining legacy levels out there, DOCSIS 3.1 out to a gig, for mid split and high split, and then being able to go into a DOCSIS 4.0 scenario where we would add the additional channel load out to 1.8 gig with the 6 dB step down or the step down. Right now, I think it's 6, but that could change with the step down that Nick talked about to maintain TCP. So what we'll end up with is a network that will be able to support all legacy stuff just as it is today, and DOCSIS 4.0, with DOCSIS 4.0 devices definitely being a single outlet home. Okay, so some of the things that we're doing to get there is, getting our spectrum ready, removal of QAM channels. I know Nick talked about that. Cox, what we did when we started going mid-split was we spectrum clear all the way to 108 megahertz. So anywhere in our network today, we are basically mid-split ready from that perspective. Even in our sub-split legacy nodes, we're spectrum clear out to support at least mid-split. And I believe we're working towards, getting ready to do that. Obviously, with high split, we have to clear that additional spectrum up to 258, where we'll have our first OFDM downstream channel there. Nodes get upgraded with high split preparation and configuration. Our amplifiers, again, with high split diplex and upstream configuration modules are done. All of our active devices are spliced. We are resplicing everything, even in areas where the form factor would be the same as the input we're putting in. The thought process there is we don't want to put a shiny brand new 1.8 gigahertz amplifier into a 20-year-old housing with 20-year-old connectors. So again, kind of that stepped approach to getting us to DOCSIS 4.0. Once we resplice these, we're aligning all of these to 5.204 megahertz. So we're doing an ingress certification process. I'm going to talk a lot about ingress, so I'll get to that. And then the last thing we'll do is we'll do service enablement for our customers, and kind of in that order. And I kind of got another slide that, now that I look at it, kind of says the same thing, but I'll cover that pretty quick. One of the things we're doing is we are using software controlled amplifiers. If you haven't seen this in the industry yet, you will. We've done a lot of training with our folks in the field, and I'll assure you that software controlled amplifiers are very new to our industry, right, in the United States. It is not new to the industry in the world. I can tell you, I was, at one time I worked for Scientific Atlanta, and I was out in Germany watching guys set up amplifiers in Germany using Craftport with a laptop with software control. But it is new to us, and we're using it to our advantage here. We're integrating these software controlled amplifiers with our Atmos as automation and tracking mobility solution, which is a tool that we use to provision nodes, RPD nodes in the field currently. I'm just going to kind of step through this very high level, but you go in there, you're going to install an amplifier. It's going to take you in, you're going to scan this amplifier, and we're going to scan the amplifier. We're going to automatically collect a bunch of information. We have worked with our engineering access engineering partners to create templates that we are actually going to load. So when you're in a market, you're going to go and you're going to go select this amplifier, you're going to get ready to put it in, you're going to select a template, and what's going to pop up are the templates that are applicable to the node that you're actually in. So you could go anywhere, if you're doing a disaster recovery across the country and you have to replace one of these amplifiers, it's going to know by the node number you're in where you're at, and it's going to present you with the right downstream configuration template, which we really like because we can do a lot of things with those templates that the technicians don't have to worry about doing. We can do, there's so much configuration. Really, for us, it's almost with the forward, it's like they're just putting the levels of the template on and checking the levels, and the amplifiers running out at the levels that the design levels for that market, and then you have to go do a little bit of alignment on the return path, of course. But you select that, and then what it does is it's going to run you through some other tool sets that I'm not showing here. And then ultimately, it's going to bring you to a birth certificate page. You're going to enter some information, and then you're basically going to say okay, and then you're going to submit that amplifier, and that'll be in our back office integration. Right, there's some other configuration things that happen there, but we've greatly minimized what the technician has to do in the field to do that. So I like that because it takes away meter variability, technician variability. Oh, I don't have a 4 EQ, I got a 6 EQ, I'll have to use that. A lot of things there, right? I mean, you can give this to anybody, and you can send 10 people in the field, and everybody's amps are going to be set up within tenths of a dB of each other. It's really good. Another thing I really like about what we're doing here is, we are now collecting this information. We'll know what serial numbers are in place. And, sometimes, it's with products out there. We all know you have issues with products, and sometimes, we'll have an issue, and, somebody will go do, we'll get with the manufacturer, and they'll go do some due diligence, and they might come back and they'll say, yeah, we had a bad component, and it went into a run of amplifiers, and here's the ones that we sold to you, and here are all the serial numbers. We can get that today. The problem is, in most of your markets, think about it, you don't know where those amplifiers are at. Tomorrow, with this type of solution, we'll know exactly where those affected amplifiers are. We'll be able to go out and make any necessary changes, right?
Hey, Mario.
Yes.
I got a question for you. So, I mean, here I see the vendors Teleste. I'm just curious, are they the only vendor that's kind of allowing this capability, or are other vendors moving this way too?
All vendors are. I try to keep this vendor agnostic, and I'm sorry if that shows up, but yeah, all vendors are kind of moving that way. They all have software controlled, and they all have their own platforms for setting up their new 1.8 amplifiers. We are working with our vendors to integrate that with our tools here at Cox.
Cool. Thanks.
Make sense? Yeah. So this is what we've done. Again, I tried to keep this as agnostic as possible. All right, so a lot going on there, but again, we're setting up an amplifier. So the idea is now we're going to do high split with those amplifiers. Now we can come back and we can go DOCSIS 4.0 by simply doing a diplex filter change and a configuration change and add a new template. We've actually done this and done some testing. Mike Cooper from our Access Engineering did a really good piece at the SCTE Expo this year. I encourage you to go look up that, talking about Cox's D4.0 testing that we did in the Arizona market. It was a good presentation. I encourage you to look at it. I talked a little bit about single outlet. Again, it's not really part of what for high split. It's not a prerequisite of high split, but we are starting to get away from that, and we're not knocking on people's doors saying, hey, we're here to disconnect all your unused outlets, but as part of professional installs and trouble calls when it warrants, and if the customer doesn't push back so much, we're starting to go to the single outlet. We like this. We've done a lot of testing on this. We feel that, obviously, I think a lot of people know that it's going to reduce a lot of the ingress potential in the field. It'll take a while to get there. It's not something you're going to see overnight. Okay. I think I'm running short on time, so I'll go. This is kind of just our, we're doing these high splits in 3 touches. If it's an analog node, we're converting it to an RPD. If it's an RPD, we go out there and we convert it to, we put in the high split capable modules, and then we, our access teams are putting on a high split prep configuration. We do some validation. We have to put LOC devices on TiVo. That's for 55 SCTE 55.1, 55.2 to convert those devices to be able to convert DSG into a local channel for those TiVo devices. So it's a converter that we're putting in. I believe all of our set-top boxes are no longer in the field. We don't really have much out there in the way of SCTE 55.1, 55.2. And I'll talk a little bit about modified profiles. We're going out on construction day. We're replacing all the amplifiers. We are removing LEQs from the network. I'll talk a little bit about that. we're setting our plant capacity and our downstream and our upstream plant capacity. And then prior to that, we're going to do some ingress certification that I'm going to talk about, and then ultimately certify that node and turn on the services for our customers. So let's talk a little bit about challenges. I know that Nick talked about a lot of this stuff, and he went into a little bit more than, sorry about that, he went into a little bit more than I am. I wanted to kind of focus this on some of the field challenges that we were going to see. But challenges, obviously, spectrum clearance to 258 megahertz. Sorry, I got a typo there, to 870 market downstream bandwidth challenges. When we're going high split, there's a brief period where we're actually losing a little bit of downstream bandwidth. We're sweeping those to 1 gigahertz, and then as quickly as possible to reclaim that bandwidth. So we haven't really had a lot of issues with that. We are removing line equalizers. Why? As part of our step to DOCSIS 4.0, we know that in DOCSIS 4.0, we really can't have LEQs out in the field. They just don't support our designs. We've been doing a lot of work in the background, testing designs, 1.8 designs. There's a lot of effort going on there right now, and none of these include these LEQs. So we thought it was a good time right now to start to remove these from the network. We standardize on our ALSC frequencies. ALSC is like an AGC, automatic level and slope control. And I know, some of our folks put a lot of effort and time in figuring out where exactly we wanted these ALSC channels to go. There's a backup and primary and backup high and low ALSC carriers. We kind of spread those out through the channel, through the downstream band in preparation for additional OFDM blocks. So, if you lost an OFDM, you didn't lose both your high and your primary and your secondary high or low pilot channels. So a lot of effort has been done there. We are actually running 2 downstream OFDM blocks now in most cases. High split sweep plans. I know Nick talked about that. We're all RPD, so in our high split, we actually have high split plans. And I know Nick briefly touched on, being able to certify that new, I call it real estate, right? So we have 2 high split plans that we run. Folks, we're going to have a BAU high split plan, which obviously don't put sweep points in the middle of an OFDM carrier. But in the interim, when you're doing that node action and we've not service enabled that, you're actually creating all this, new real estate that, it's blank. So what we do, we have a special high split engineering plan where we started putting sweep points every 1 megahertz, but I got a little pushback from the field. So, between, our legacy band and that, that 85 to 204 megahertz, we're putting sweep carriers every 6 megahertz. So we can get a real good look at the return, spectrum that we're, our new real estate to make sure, it's good. We don't see any issues with it. So that's some of the stuff that we're doing. And that's really all I'll talk about. We're not, again, we're all RPD, so we're not having the units and the head end units. ACI concerns, adjacent channel interference or customer interference, what he talked about, our teams have looked at that as well. I know Nick did a really good job talking about that with you folks, and talking about the filter availability. We do have part numbers for those if we need them. So we are prepared for that, should that become an eventuality. Hopefully we don't have to use a lot of that. One of the things that we've been doing a lot at Cox is in this journey to 4.0, kind of keep referring to that because this is a step in that process, is trying to remove what I like to dub split limiting devices in customers' homes. You got to have house amps. So we got mid split, high split house amps, but there's a lot of things, like, reverse attenuators, LEQs for the homes, things that are, sub-split, mid-split, high split. We're trying to get those out of our network, right? So we can actually grow our network and not cause a bunch of problems in customers' homes. So some work is being done there, okay? So on the upstream, we're kind of, well, here's what we differ just a little bit from what Charter's doing. So we are actually doing a 6 dB step down on our 85 to 204 OFDMA channel. And we don't have to do this for high split. This is another step in preparation for ultra high split 396. We know that there could be some TCP issues, some transmit level issues. If we tried to maintain these levels, we will have to step down future OFDMA blocks above 204. So we are just kind of getting ahead of the game and doing a step down now. So it's a little bit of a trade-off. We're giving a little bit of MER performance there away with our step down, but we haven't seen any real issues with that yet. A little bit different. I know Charter said they do 11 dBm per channel. Our N plus X is 13 dBm per channel. We kept that because that was our design that we went with mid split. So we wanted to keep things as much as the same as possible. We had a lot of discussion. We determined we were able to do that. And the 11 dB is for our node 0 stuff. All right. Again, so we that's kind of what ours is going to look like. And does look like in the field. Test equipment measurements, this gets a little kludgy, right? Because now, you know, we had a lot of discussion. Historically, our tools, when you look at ATDMA carriers, our tools have always corrected and showed you channel power for the corrected bandwidth. Meaning, if you had a 3.2, we corrected the bandwidth, you know, and the transmit level for that 3.2 carrier or that 6.4 carrier. The CMTS measures everything in 1.6 megahertz wide bandwidth. So we had a lot of discussion. This is really back, you know, when we started talking about doing OFDMA. How do you transition that, right? You know, we wanted to keep things the same for our technicians. So if you're used to seeing, you know, a transmit level on a 6.4 at X, that's fine. But with OFDMA, we introduced, you know, there's going to be a 6 dB step down that you're going to see on your equipment. It's running at the same level. The difference is we're measuring it in a 1.6 megahertz bandwidth versus a 6.4 megahertz bandwidth. So you'll see about a 6 dB difference in apparent transmit level. And now when we go to high split, you're going to see about a 12, and you can see that here on this. See if I can get my little pointer working. Yeah, you can see that here on the meter here, and it also reflects in our tools as well. So we tell our folks, hey, you know, do what you do, you know, keep your transmit levels with your ATDMAs, and these things are going to fall into place, and then you can just, you know, do it in your head. You know, most time they'll see that 6 dB delta. It all depends where you're at in the network, whether that's going to be a perfect 6 dB delta or not. That's a whole nother discussion. But the thing is, with our meters, there are 3 different ways you can look at that. You can look at that in, you know, correcting the OFDMA to 1.6 and leaving the ATDMAs alone. You can do it with, you know, everything at 1.6 megahertz wide carriers, or you can correct everything to 6.4. So we kind of took this hybrid approach to try to get our technicians, you know, to learn, because eventually, you know, one day, I don't know, I'll probably be retired, but you know, ATDMA may go away and it'll be all OFDMA, and we're just going to transition into that new measurement, you know, mindset. Okay, so we've had to do some training on that as well, and I don't think we've run into much issue with it. All right, sorry. Okay, so let's talk a little bit about return challenges with high split. So I kind of breezed over a lot of stuff. I know Nick did a great job of filling in some of the gaps that I didn't really speak about. And I'm going to talk about something that I know he probably wanted to talk about as well. But we've done a lot of work looking at these return path challenges with what we call OTA interferers, over-the-air broadcasters. Okay. So, you know, some of the impacts on performance and what we're doing to combat that here at Cox, and some of the new processes that we're implementing. Okay, so, you know, when you look at the SCTE spectrum allocation, you'll see, you know, it's packed in there with stuff, even in the bands that we use, you know, and for the most part, you know, we don't see interference with all of these different items, these licensed spectrums that folks can use. With our legacy stuff, it's always been with the ham radio, the shortwave AM radio problems, impulse noise, things of that nature, the ramp up, I like to call drop noise down there at the bottom. But when we started going to mid split and high split, we knew right away that we're going to be contending with a whole new part of interference, and that is in the form of off-air broadcasters. So now, think about your markets where we're at. We've got broadcasters with 50,000 watt transmitters transmitting right on top of the spectrum that we're going to use, right? So when you look at where we cover up from sub-split, mid-split, and high split, we now have to deal with low band VHF channels 2 through 6. With high split, we have to contend with high band VHF channels 7 through 11. High band's actually 7 through 13, but a couple of those channels fall outside of our band. So those are things that we're going to have to deal with. This was a learning experience for me because I started to dig into this, and you'll see some of the work that we did. And I expect, I knew with the digital transition and television broadcast, I was under the impression that all broadcasters were going to have to vacate the VHF spectrum, low and high band VHF spectrum, and move to UHF. Well, apparently, I think they've got a reprieve on that. It's a government thing, so who knows how long that reprieve. I was a little bit shocked to find out how many off-air broadcasters, and I'll just give you a couple of quick numbers. We have 68 total individual broadcast television stations that can interfere with our markets, both high and mid split. And our high split, 52 of those are in our high split spectrum, right? And some of those, those are individual channels, and some of them, can go across markets, and we'll talk a little bit about that. Okay. So our current spectrum allocation here looks something like this. We have our 5 to 40 megahertz down here. We got a 45 megahertz OFDMA channel. You have the FM band and the aeronautical band. So initially, what we're going to do when we do high splits, we're going to put a 66 megahertz wide OFDMA channel there while we work through the OUDP. Getting all that configuration on the back end. But the problem you have there is you have all of these channels that kind of sit right in the middle potential of your upstream spectrum. I'll let you know, from what I've looked at. Cool thing here, I'm sitting in Atlanta. I know a lot of you guys are sitting in Atlanta. All Atlanta broadcast television are all up in the UHF. I think there's one in our Macon market we have to contend with, but so you get a little reprieve there. But that's not, I would say think about it across other markets where you might have these issues. Okay, so what we'll do is we'll talk about how we're gonna combat that, and then eventually with OUDP we're gonna have a 96 megahertz wide channel sitting there, and that's kind of the band plan, at least how I know it today, as what we're gonna do. Okay. And we can probably get a total throughput capability of about 1.3 gig in the upstream. Okay, so let's talk a little bit about some of the impacts of these OTAs, over-the-air broadcasters. We've done a lot of testing. I know Access has, and we have, and working with the field to figure out exactly where, how much ingress we can tolerate, because it's kind of difficult when you're, maybe in the shadow, and sometimes not necessarily in the shadow is the worst place to be in a tower, but to be maybe 5-10 kilometers away from that tower. It's how much effort does it take to keep these nodes clean with these off-air broadcasters. We want to maintain a minimum of 33 MER on our OFDMA carriers. So I can't really read this, but I think we've got down to about minus 28, depending on our node vendor, because they measure a little bit different. But we have a sweet spot, and let me just say that, where we want to see that ingress interfering carrier be below. And what happens is when that interfering carrier gets higher, it starts to affect the OFDMA subcarriers, and we all know that when part of that channel is impaired, the whole channel is impaired, and it starts to cause profile issues for us. And then you get into the place where you're not running optimal profiles that we want to see. Okay, so we'll talk a little bit more about this, how Cox is actually combating that, and I'm sure Charter is as well. So what does this ingress look like? There's some of our desired carriers. You guys are familiar with all this. You can see the telltale, what looks like 6 megahertz wide, 8 VSB carriers, because they're all digital down there today. Those are the things we knew about. We did a lot of planning for those. We all know about the FM band. I think I'm not sure what our plan is yet. I'm sure what PMA will be looking at using the FM band eventually as well. We know that this is a very hostile area to work in, of course, and I know in our markets, I think Nick alluded to it, you can't, the whole FM band is loaded, even out in some of the rural areas, right? Some of the things we've learned about, there's things that we know, right? We know, hey, we were able to look at what all of these ingress sources are going to be. There's things that we know and things that we didn't know. With mid-split, we started seeing interference with our set-top boxes, where somebody might have accidentally hooked the set-top box wrong, and we got a back feed on our system, and you see what looks like this little trident. I like to call it the Three Sisters. We knew exactly what we were looking for there. 8 VSB broadcaster interference. Okay, so what are we doing about this? So we're starting to use what we call unused bands. So we've done a lot of work here to kind of keep this so we don't have a whole crazy amount of configurations. We have 2 configurations. We have this says mid-split, high split. We have a full band profile and a modified profile. And what the modified profiles do is they create an unused band in areas where we know we have interference, and these are problem areas that we know we're not going to be able to keep clean. Okay, so what these look like is you'll still see MER probes running across that, but the actual traffic, the mini slots that are in that unused band are not assigned to a modem to use. Thus, we're kind of steering around some of this interference. We hate to do it because you would say, let's go clean up the ingress. Well, yes, let's clean up the ingress, and that's what we're doing. But there comes a point in some cases where it's just cost prohibitive to do so, and so sometimes it's just easier to give up a little bit of that bandwidth. And let's say, I'm just going to give you an example. On a 45 megahertz wide OFDMA carrier, sometimes it's better to run 39 a 39 megahertz of bandwidth getting 2048 QAM than 45 megahertz running 256 QAM, right? You're getting more throughput. So there's a trade-off there that we're working from. So what we've done is we've created these modified profiles, and I'll show you a little bit of our methodology. What that means is, in any given market, when an engineer goes to put service enablement on, they're going to know I'm either going to do a full profile or a modified profile. They don't need to worry about what channels, what frequencies. We've done all that for them. All they need to do is select that profile, 21 or 31. Those are our modified profiles, and it doesn't matter if you're in our New England system or out in Southern California. The profile number is the same, but the channels that we that we steer around, the frequencies that we steer around are different, and they're specific to the market. Okay, so we did a lot of look at this. Spent a lot of time looking at OTA interference. A tower site, depending on average height above terrain, where that guy sits. Here I'm showing our Hampton Road, so that's pretty much sea level. You might have a tower site that's probably a pretty tall tower there. You might have a short tower on a mountain, but depending on tower height and power, radiated power, you can get roughly 45 to 70 miles. We did a lot of calculations on this, and it really works out to be about that. And the curvature of the earth starts to come into play, and again, so we had to look at that. So that's cool, right? But it's not just one channel. In some cases, it's multiple channels, and the way our markets are spread out. I went to, and I put this down here, man. This is really cool. Sorry about that. This is really cool, but I put http www.tvfool.com. I recommend you go look at that site. This is where I pulled these really cool heat maps, and there's all kinds of stuff you can do with this, but I kind of made a compilation here of heat maps just kind of show you where, in some of our markets, where these channels are. And we really had to get granular on these. And if, I actually did some rough calculations based on, height and tower, power and height above terrain. And, I had circles. I had a map on Google Earth that had circles drawn. And then when I actually found this TV Fool, looked at these heat maps, that they fit right in the middle of the circles perfectly. But some of the things we had to look at were some of our markets are in close proximity to one another, and we had to figure out, like Oklahoma City and Tulsa, they're probably far enough apart you can see that they don't too much interfere with each other. But there are chances in some other markets that we have, or Tulsa, maybe in our Northwest Arkansas market, sorry about that. In our Northwest Arkansas market, there could be some overlap of these channels. So we actually got as granular as we could down to the hub site and said, hey, can this hub, what channels can this hub have? And then what we did was we built a matrix, to kind of get a big, look at, where these interferes are on which hub sites. Went over and built this into, what actual off-air channels and what frequencies needed to be included in these unused bands. And then working with our access folks, our engineer extraordinaire took these things and built these custom profiles for our access folks to put out there when needed. Okay, so it's been a real good team effort. It's worked out really well. These are things that we know about, right? And we've done a lot of great work here. And we've had one or two channels crop up on us. We had a new channel 6 in Las Vegas. We had a market in our Roanoke market where we had another channel crop up that did a retransmission from another city, where we've had to modify these modified profiles, so to speak. But for the most part, we've been spot on. We had one location where I had a channel out of Boston that really wasn't a problem, so that was good. We got to take that one off. Some of the things we don't know, guys, and and with mid-split we learned about like municipalities and radio communications. We've had some issues around 44 megahertz. We've had problems with like hospitals and schools. They use clock synchronizers. Think about a school. Every classroom's got a clock in it. There's a synchronizer, and they're usually about 72 megahertz. That puts out a signal, for like 45 minutes of every hour, synchronizing all their clocks. They've caused us some issues as well. So we've had to make some adjustments to some of these modified profiles, but we've tried to minimize it, as much as we possibly can, rather than trying to do blanket stuff. Where did I get a lot of this information from? I did a query, and I'll get this to Jason. I got a spreadsheet that I'll just share with you that I went to FCC, and I basically said, show me every single television and FM station in America and Canada and Mexico, by the way. And then I went in there and I sorted them by what was, what meant something to us at Cox, and you could do the same thing with it. And I've done some of the work. I'm glad to share it. Okay, so we've created these modified profiles. We've got them all ready. Now we have to take, and I'm almost done here, so I know I'm running a little short. We've taken a kind of a new approach to launching OFDMA. So I'm going to shift you to the right side. One of our prior processes, and this has kind of been in the industry, right? Construction goes out and builds something. We do proofing of that new construction. We hand it over and say, there you go. You got new real estate. Go do what you're going to do with it, right? And that's kind of been probably what a lot of folks do, and it's not wrong. But we realized pretty quick with OFDMA that we needed to probably take another approach. We needed to sandwich a new process in here. And we needed to, instead of going to instead of going right to service enablement, we need to really get our outside plant folks in here to certify these nodes for ingress. So it started out as, hey, a process, that we were going to do this and get these, sandwich our operations folks in the middle of a construction, between construction and access, actually service enabling this. And then this kind of took off from there, in partnership with our access team. Again, there's always a partnership down here. We brought in some, really super smart kids from our automation team, and then they built this entire dashboard. And I'm going to talk a little bit about that. And then, we built a dashboard. So what happens is we do a plant enablement, we finish enablement, we go back to that Atmos, that what I showed you earlier, where we can go in there, we can provision nodes and amplifiers. Well, in that Atmos, there's also, when they get done doing a service and plant enablement, in other words, upgrading to high split, they will go in there and they will set the plant capability, and they will set that plant capability to what we call the 52204 INV. And that goes into some of our back office tools. So, and what happens is our access people who are enabling services are looking at this back office tool, and they're either going to see 52204 or 52204M. And that means that node needs to be provisioned with 52204 full profile, full 66 megahertz wide OFDM A carrier, or the modified profile. They don't need to ask. Jim don't need to talk to Joe. I don't need to send emails, and there's no lost in translation. They know that if they see 52204, it's full profile. If they see 52204M, it's a modified profile. If they see 52204 or 5to85 INV, that means that node is an investigative, I'd call it purgatory, right? It's sitting there and it's being investigated for ingress, and they don't do anything with that until we disposition that node. So what happens is we do completion, the field evaluates this, we ticket any ingress for cleanup, and then we will select a full or modified profile, and then that gets sent, then that we change that profile from 52204 investigate INV to 52204M or 52204, and that tells the folks who are doing these upgrades, these service enablements, they can go ahead and do that, and it takes a little bit of that human element out of it. Right? So we built a cool dashboard, we as in our smart kids, where what happens is when these things go 5to85 or 52204 investigate, they go right into this dashboard. And then our folks will monitor this dashboard, and they will look at these. Initially, they would look at these nodes, and they would validate, yes, it's bad, no, it's good, or yes, and then a human would go in here and actually determine, okay, I need to ticket this node for ingress, and then wait for the ticket to come back and say, okay, did I fix the ingress? Can I, can't I? Do I need to set this for a full or modified profile? And they would do it in this dashboard. This dashboard still exists, but we've added another element because things, great people doing a lot of great work. We've done some automation that we're just now launching as well, where when a node actually gets triggered from the field, so when the guy in the field, the project manager says that's 52204 investigate, it will trigger a automated ingress check, and it looks for CPD, chronic noise node status. In other words, is this node in one of our tool sets that's a problem child node? And it will look for ingress. And we have some rules set in there for ingress and these things. It looks for these three things. If the node is clean, it will automatically push that through to our back office systems and say 52204, right? So we don't have to touch them. The only ones now that are coming into this dashboard are the ones that fail that automation check. Keep in mind, we all know it's a snapshot in time. It could be perfect today, bad tomorrow. We know that, but at least we're looking at this. And the idea here is to let's look at these nodes so we don't cause undue stress and a bad customer experience and a bad operations experience, right? Let operations get a chance to, help control their destiny and work on some of this ingress and do what we can to fix it so we don't get flooded with calls. And this process has worked fairly well. I haven't heard of any. I was, really involved on the front end, but now it's operationalized. I haven't heard a lot of issues, with customers, and we're using this for mid-split as well. So it's really helped us, right? And so this, this is how this has grown from an idea that said, hey, we need to talk, we need to, change our process to today where we've got all this automation. I think that's a whole lot of information. I know I was running a little short on time. But are there any questions?
Mario, I don't see any at the moment, but great job. I know that was a lot of content, but a lot of really interesting stuff. Especially, the on-the-air maps. I've never seen anything like that. I thought that was really cool.
Yeah, that's why this morning I'm like, you know what? I'm going to put that link on there because I know when I found out about that, that's a super cool website to go to. So.
Yep, I have it up on my second monitor right now. Let's take a look at it.
All right, if there's no questions, you can always hit me up again. As a board member in the SCTE chat, thanks to our prior speakers, and thanks for giving me the opportunity to speak today. I appreciate it.
Yep, thanks a lot, Mario. And one thing, I was looking at all the bios of our three speakers. They have over 100 years experience between the three of them. So, pretty evident. You guys are extremely knowledgeable in what you do, and I know you're all approachable. So if anyone does have any questions, feel free to email them.
Yeah, I thought it was funny. I thought I had a lot of MSOs under my belt till I heard Frank's bio.
Yeah.
Good stuff, man. Thanks, everyone.
All right. Thanks a lot. Until next time.